Okay, well, before I continue with what I was talking, you see there was this point where I wanted to evaluate L33 rho, and that would be defined as d to the power of 3 by d rho to the power of 3 L3 rho. And L3 rho itself involves differentiations. So, L3 rho we saw that it is given by this expression, but there are 3 differentiations of this object which is tedious, and therefore, I did not do it in the lecture, but I can get a software like Mathematica to do the differentiation, and all that I have to do is write these simple commands and I get the answer. The answer is actually 6 minus 18 rho plus rho 9 rho square minus rho cube. So, this you will have to put in here. So, this is actually 6 minus 18 rho plus 9 rho square minus rho cube. So, that is this object, and then you have to carry the 3 differentiations of that. When you carry 3 differentiations, you will see this is going to be 0, that is going to be 0, this also will be 0. Only this term will give you a non-zero contribution, and that is going to be minus of 3 into 2 into 1, that is all. So, therefore, what is the answer? Minus of 3 into 2 into 1, it is minus 6. So, this object, if you evaluate it using all these formulae which looks complicated, you get a simple answer, it is minus 6. So, this minus 6 you will have to put into the expression for the wave function, that is all. So, coming to the question that I was asking you, what is the probability that that the distance of the electron from the nucleus is between 5 and 5.01 angstroms. Okay. Again, before I discuss that, you see it is possible for me to use Mathematica and to produce this kind of density plots for the wave function, and that I have here in this picture. Okay. This is a density plot, it is not exactly done the way I have told you. The Mathematica has put its own color, but if you look at the plot, you will see that there is a concentration of density right in the middle, and as you go away with this is actually color coded. So, far away you will realize the blue actually corresponds to 0 in this picture. So, far away the wave function almost is very small, and as you approach the from infinity, let us say, you can see the value here. If you see where the value is actually 0.047 value of the wave function, and here it has increased, the value is twice the previous value, and then when you get closer, you find that the value goes on increasing, and not only that, anywhere along this circle what will happen, the function is spherically symmetric. So, it has precisely the same value, and as you approach the nucleus, you will see that the value of the function goes on increasing, right. So, that is what I was telling you, but now going back to this question, I want to generalize and I want to ask, what is the probability that the distance of the electron from the nucleus lies between r and r plus dr? How will I answer such a question? Well, if you say that the distance of the electron is equal to r, where will the electron be? It can be anywhere on the surface of a sphere having radius equal to r. Or if you said that the distance is r equal to r plus dr, then that means that you have to think of a slightly larger sphere. Let me just draw these 2 spheres on the board. So, here is my first sphere, it has a radius equal to r, and here is my second sphere. Okay, I mean this is not such a nice second sphere, but this is the best that I can do, and this has a radius equal to r plus dr, and therefore, the thickness of this part, this is how much? It is dr obviously. And so, therefore, you see if you say that the distance of the electron is between r and r plus dr, it actually means that the electron is anywhere inside this spherical shell. It is inside anywhere inside this spherical shell. I want to mark that spherical shell. So, if it lies anywhere inside this spherical shell, its distance is between r and r plus dr. So, if you wanted to calculate the probability that the electron is in that region, what should you do? Well, first of all, you will have to evaluate the wave function inside the spherical shell, but for any point inside the spherical shell, what will happen? The distance is the same from the nucleus, and therefore, the value of the wave function here or there, it is going to be the same, and over the distance of the spherical shell, because dr is a very small amount. So, therefore, what is going to happen is that over this distance, the wave function is not going to change much. It will change slightly, but I am going to neglect that. So, anywhere inside this, what is going to happen? I will have to evaluate the wave function. What is the wave function? It is actually 1 by a0, I do not remember it exactly now, but I will write from my memory, you can correct me if I am wrong. This is my wave function. This is my psi 1s. Yeah, I understand. There is a 2 here. This is my wave function. So, see within this spherical shell, I can evaluate the wave function anywhere, it is going to be the same. So, what I will do then is, I will take the wave function, but I am interested in the probability. So, therefore, I will calculate the probability density, which is the square of this function. Probability density is the square of the function, and then what should I do? I will have to multiply it by the volume of this spherical shell, because the more the volume is, the more is the probability. So, what is the volume of the spherical shell? Well, that you can easily realize by remembering that, see, a spherical shell has only a small amount of thickness. So, if you multiply the surface area of the inner sphere by the thickness of the spherical shell, you will get the volume of the spherical shell. Surface area of the inner sphere is how much? It is 4 pi r square. So, you take this, multiply this by 4 pi r square, and then the thickness of the spherical shell, as I have told you, is dr. So, therefore, this is the surface area of this inner sphere and thickness of the shell, that is dr. So, you multiply these things, you are going to get the volume of the spherical shell, and this product is what you refer to as the probability. This is your probability that the distance is between r and r plus dr. It is not at all surprising that there is this dr, because if the spherical shell thickness increased, the probability has to increase. So, therefore, it has to be dr, and the dr has to be there. So, what I am going to do is, I am going to say, okay, I am going to define some function. What do I call it? By some name, that thing multiplied by dr is actually equal to psi 1s 4 pi r square dr, and therefore, I can define this object to be a function that is interesting. It actually tells you what the probability is that the distance of the electron from the nucleus is equal to r. It gives you an idea of how probable each distance is, right. So, this object is referred to as the radial distribution function. And suppose I made a plot of this radial distribution function. What does the radial distribution function give you? It gives you an idea of how probable a distance r from the nucleus is. That is what it says. So, if you make a plot of this object, what would be the result? Let us look at that result. What is it actually? You take this, square it. When you square it, you are going to get 1 by a0 to the power of 3. Then you will get this square of this, which is going to be 4 e to the power of minus 2r by a0, 1 by 4 pi. This is the square of the whole thing. You have to multiply this by 4 pi r square. So, naturally this 1 by 4 pi and that 4 pi will go. So, the function actually is quite simple, it is just this. And suppose you make a plot of this against the distance r. What are you going to get? This is a radial distribution function, which is actually nothing but 4 pi r square psi 1s square. This is what the object is. So, if you look at this function, you will realize at small distances from the nucleus, r is small. So, what will happen? The function will have a value which is very small. Why is it so small? Well, the answer is, you see, you have to remember, suppose I asked you what is the most probable position for the electron, what would be the answer? The most probable position is the position where the wave function has the largest value, and that actually in this case is at the nucleus. That is the most probable position for the nucleus, for the electron, right. Now, what I am saying is that I am asking what is the probability that the distance of the electron from the nucleus is equal to r. I should say probability density, that the distance is equal to r. Then what do you find? You find that you have this r square. So, because of this r square, what will happen? When r is very small, the function will have a small value, and when you increase the value of r, this function r square is going to increase. So, it will increase like this, but the increase cannot go on forever, because you have this e to the power of minus 2r by a0. So, that exponential term, what will it do? It will cause the function to decrease. So, eventually what will happen? The decrease in the function will become very important, and you will have such a behavior. Now, in this region what is happening is that you remember you were calculating the surface area of the sphere. Surface area of the sphere is 4 pi r square, and the smaller the sphere is, the smaller is the surface area. That is the reason why this r square is actually occurring in there, correct. And because of that, if you made a plot of the radial distribution function 4 pi r square psi 1 square against r, what do you find? You find that near the nucleus it has a value which is very small, but as you go away from the nucleus the value increases, it reaches a maximum, but then of course the wave function has to decrease. So, eventually the probability density that the distance of the electron is equal to r decreases, it becomes 0 at infinite distance. So, there is a most probable distance, and this most probable distance is this one, and I want to find this most probable distance. How will I find that? You can use methods of calculus. How will you use the methods of calculus? It is actually extremely simple. This is the plot, this is the function that you are plotting. You have to differentiate this with respect to r, put the derivative equal to 0, and find that value of r at which the function is a maximum. Simple exercise in calculus, and you will find, I am not going to do it because it is quite simple. You will find that this most probable distance of the electron from the nucleus actually is equal to a0, radius of the first Bohr orbit. Now, here again I want to tell you something. You see, according to the Bohr theory, what was happening is that the electron was actually moving in a circular orbit, right, and the radius of that circular orbit was actually equal to a0. That is what Bohr said, right. Now, this is very unsatisfactory if you think about it as a chemist, because that would imply that the hydrogen atom is like a plate, is it not? I mean, it is planar. If you had a circle and the electron was moving in a circle, it is actually like a it is a completely planar thing. And I mean, suppose you are a chemist, you say, okay, I have two hydrogen atoms approaching. Think of the reaction. I mean, suppose this is one hydrogen atom, this is the other hydrogen, and the two approach, they can approach like this, they can approach like that, then things will be different, right. But that is not what is happening in this picture. In this picture, each hydrogen atom, suppose you think of the hydrogen atom, the electron is sitting in the ground state, each is sitting in a 1s atomic orbital, each electron. 1s atomic orbital you have seen is spherical, so it is something resembling a sphere and two spheres approaching each other, right. Whether they approach in this fashion or whether they approach in that fashion, it is all the same, right. And that this is a much nicer picture, of course, and of course and also the correct picture. But coming back to the Bohr theory was saying that the orbit is maybe a circle like this. Maybe I can draw this, a circle of this form, and the radius actually is equal to a0. This is what the Bohr theory says. But according to this, what happens is that you see a0 is only the most probable distance. If you ask what is the most probable distance of the electron from the nucleus, it is a0. But there is a chance that the distance will be less than that, and there is also a chance that the distance will be greater than that. That is what the Schrodinger's wave equation is telling you. Fine. Now we will look at other wave functions. We will look at the case where n is equal to 2. So if you have n equal to 2, what will happen? If you want to calculate the energy of the system, it is very simple. You just have to put n equal to 2 here. That is all, right, and you will find that the energy is higher than previously. In the previous case, you had n equal to 1, and so therefore this is a higher state. In fact, it is the what is referred to as the first excited state. In fact, maybe I should draw a picture. If you put n equal to 1, you will get this as the energy, n equal to 1. If you want to calculate the energy, you just have to use this expression, just put n equal to 1 in there. Then n equal to 2 is somewhere here, n equal to 3 will be somewhere here, n equal to 4, 5, 6, 7, 8, 9 and so on. As the value of n increases, what happens, you see, you have this 1 by n square. So what will happen is that the energy actually, the levels get closer and closer and closer, right, until n is equal to infinity. If n is equal to infinity, what will happen? The energy actually according to this will become 0. So therefore what happens is that the energy levels actually approach each other, they get very close. In the limit n tending to infinity, the separation between the allowed energy levels is actually becoming very small. It will tend to 0 as the value of n approaches infinity. So below 0, you have how many levels? Infinite number of levels are there, right, for the hydrogen atom. Infinite number of levels are there, or infinite number of atomic orbitals are there in the case of hydrogen atom. Remember my discussion of how many normal modes of motion for a string. I told you that there were infinite number of normal modes of motion for the string. It is exactly that what is happening here, right. These are, remember, these are all actually stationary states or standing wave patterns formed by the electron wave in space. These are that is what it is. So if you ask how many standing wave patterns are possible, the answer is infinity, and that is precisely what follows from solving this equation. So this is how the allowed energy levels are, and as I told you, I am going to look at n equal to 2. N equal to 2, what will happen? I would have psi 2. If n is 2, our conditions imply that L has to be 1. So L will be 1. Oh sorry, what are our conditions? N is equal to 2, L may be 0 or 1, L equal to 2 is not allowed. So, let us think of these possibilities. N is equal to 2 and let me say L is equal to 0, and if L is equal to 0, M is 0. So, this is the function that I want to look at, and obviously this is going to be R20 of small r y00 of theta phi, that is what it is, correct, because L is 0 and M is 0. So, the function, the angular part is just y00, but y00 is something that we are already familiar with, because in the case of the 1s atomic orbital we wrote this down, we found that it is actually 1 by square root of pi 4 pi, this part is 1 by square root of 4 pi. And R20 you can evaluate using the formula that we have. Okay, for example, R20 is written here. Okay, R20 is written there, you can make use of that, and what will happen, you will get the total wave function. So, I think the total wave function is there in the slide. Okay, this is the wave function that is appropriate for the 1s. We have already discussed this, so I will not discuss this, but if n is equal to 2 and L is equal to 0, this is the function, right. You have determined the angular part, you have determined the radial part, multiplied them together, you get this as the answer. But what is most interesting is that you find the function y00, and what is that? It is 1 by square root of 4 pi, and this obviously or immediately tells you that this function has no direction dependence. So, this function also is going to be spherically symmetric, this particular function. Not only this function, if ever you had a case where L is equal to 0, right, if L is 0, what about the value of M? M has to be 0, and the function that will occur as the angular part will be just 0, and so it will be y00 theta phi, and it will always be this 1 by square root of 4 pi, it will not be anything else. So, whenever L is equal to 0, you find that the function is spherically symmetric, right, and it is not necessary for me to discuss the angular dependence, because we have already done it. So, what is left is to discuss the radial part, and if you look at the radial part, it is obvious that it has this form, right. I mean, this part is a constant, and you have the r 2 minus r by a0 e to the power of minus r by 2 a0, that is the function. Okay. So, how will the plot of this function look like? Psi 200 is equal to a constant. Well, we are not terribly interested in the exact value of the constant, but what is more interesting is that 2 minus r by a0 into e to the power of minus r by a0. This is the object that is of great interest, because this tells you how the wave function changes as you go away from the nucleus. So, first we will make a plot of psi 200 against r. What will you find? Well, this part is a constant, it occurs in for all values of r. So, this we are not terribly interested in this part, but you look at this part, if r is equal to 0, what will happen? This is equal to 0 and this is equal to 1. So, the function will have the value 2. So, the function is actually non-zero and it will start somewhere here, and as you increase the value of r from 0, what will happen? 2 minus r by a0 is going to decrease, and this also is going to decrease. So, therefore, the function will start decreasing, and in fact, when r is such that it is equal to 2 a0, suppose 2 times the radius of the first Bohr orbit, what will happen? You will have 2 minus 2. So, the function will be 0. So, this will actually decrease to 0 at this point. And beyond this point, if you are to this side, what will happen? R is actually greater than 2a0, which means that this object is going to be negative. So, the function becomes negative, and as you go further, what will happen? Well, you see, this is definitely going to decrease to 0 as r tends to infinity. So, therefore, it cannot go on decreasing like this, eventually it has to turn around and become 0. So, this will be the plot, right. This will be the plot of the wave function against distance. So, what do you find? At a distance of r equal to 2a0, the wave function becomes identically equal to 0. So, you say that there is a node for the wave function. Where is that node? Node is just the point where, or a point where the wave function becomes 0, you say that is a node. So, r is equal to 2a0 is the node. So, when is it that r is equal to 2a0? Answer is, you think of any sphere, sorry, not any sphere, but you think of a sphere having radius equal to 2a0 centered at the nucleus. Anywhere on the surface of the sphere, r will be equal to 2a0, and on the surface of that sphere, the wave function will be identically equal to 0. And within the sphere, what will happen? The wave function will be, within the sphere, r will be less than 2a0, and therefore, you are in this region. Within the sphere, you may be somewhere here. So, the wave function will be positive, while outside the sphere you are in this region, and there the wave function will be negative. And therefore, if I wanted to represent this wave function by shading, how will I represent the function? Okay, let me say here is the nucleus, and this is where the function is positive. Positive region I will indicate with this color instead of putting plus and minus. I mean, I will also put plus and minus, but let me put this color. So, this is how the wave function is. In fact, as you will have realized, the wave function has a non-zero large value at the nucleus. As you go away from the nucleus, the function decreases. Here is the sphere having radius equal to how much? 2a0, r equal to 2a0. There the wave function actually becomes equal to 0. Inside, the wave function is actually positive. What about outside? Outside, the wave function is negative, and I will indicate that with the green color. And as you go away from the nucleus, what will happen? The wave function will steadily go on decreasing, but of course, it will become 0 only at infinite distance. So, in this region, the wave function is negative. And so, this function has a node. The node is actually the surface of a sphere of radius 2a0. Okay. Now, if you want, you can take the square of this function, say that that is the probability density, and make a similar plot. How will it look like? Well, when you have taken the square, you see the square is going to be positive everywhere. So, therefore, I will just use chalk of white color. This is the surface of the sphere of radius 2a0. Outside, again the wave function has a positive, I mean the square has a positive value. So, therefore, this is positive, because it is density, I mean I do not have to put the plus or minus signs, because I know it is positive always. So, but the thing is, on the surface of the sphere, again the square also will become 0, right. I can also make a plot of the radial distribution function. What will that be? It is going to be 4 pi r square psi 2 0 0 square. How will you make a plot? Well, it is fairly simple. all that you need to do is take this function, put it there, calculate 4 pi r square into that square and make a plot. Well, we can think about it. You see, if I see this is the point 2 a 0, there the wave function will become 0. So, naturally its square also will become 0. In this region what will happen, the wave function is positive and non-zero, but at the origin 4 pi r square term will make the product equal to 0. So, therefore, it will start with 0 here, it will increase to some value, then it has to decrease to 0 at this point, because there the wave function is 0, and then beyond that what will happen, the function still is positive. So, it will increase to a larger value perhaps, and then it will decrease. So, this is how the plot of 4 pi r square psi square for this particular case is going to be. And then suppose you are asked the question, what is the most probable distance of the electron from the nucleus, what will be your answer? Well, you can say, well, if you did calculus, you will be able to find the maxima of this function. So, what you do, you take this function, differentiate it with respect to r and put the derivative equal to 0, find the answers. You will get two values of r, one will be this one, I do not know how much it is, you can easily do it, it is not a difficult thing. You can find this value as well as that value and say, okay, there are two most probable distances, one is this one and the other is that. And among the two, which is more probable, answer is this, it is the second one. Right, that is what actually happens. This is the one that is the most probable distance. So, remember this plot that I had shown you, this is for the 1s atomic orbital. I can make a similar plot for the 2s atomic orbital, I think it is here, therefore, I would like to show you if it is here. No, unfortunately it does not seem to be here. So, okay, now let us look at the case where n is equal to 2, and L is equal to 1. So, n is 2, L is 1, and what about m? Remember, m is constrained to be, this is the condition. So, if L is 1, m can be 0, that is a possibility, or it may be plus 1 or minus 1. So, therefore, you have psi 2 1 0 as one solution, you have psi 2 1 plus 1 as another solution, psi 2 1 minus 1 as the third solution. So, I am going to have 3 solutions, but then if you looked at all these solutions, all of them have n equal to 2. If all of them have n equal to 2, what will happen? You look at the expression for energy, energy does not depend upon the quantum numbers L and m, it depends only upon n. So, if it depends only upon n, what will happen? All these 4 solutions have precisely the same energy. So, corresponding to that particular energy, we claim that there are 4 different solutions of the Schrodinger equation. So, we say that this particular energy level is 4-fold degenerate, degeneracy is 4-fold degenerate, because there are 4 states, and we will look at the state psi 2 1 0 today, and then we will look at the other 2 later. Okay. So, psi 210, what is the form of psi 210? You can evaluate it using the formulae that are there on the board, but we will not spend time on that, we will just look at the expression. This is the expression, okay, let me. This function we have already discussed. When n is equal to 2 and L equal to 1, you can have the function psi 210, and what do you find? You find that there is this radial part of the function which is written here. There is the radial part, there is also the angular part, and interestingly this time the angular part is not a constant. Earlier it was 1 by square root of 4 pi, but here the angular part is not a constant, and you find that actually the angular part has the term cosine of theta. So, therefore, what will happen? You realize immediately that this is a function that is going to depend upon direction in space. Okay. But before you look at the direction dependence, you can look at the radial dependence of the function. The radial dependence is how you see the radial dependence. There is this r and e to the power of minus r by 2 a0. So, therefore, the function except for a constant, the function has the form r by a0 e to the power of minus r by 2 a0. That is how the function is. Okay. So, this is the radial part of the function. This is actually r21, n is equal to 2 and L is equal to 1. The function is proportional to this. There is some factor here which I am not writing. You can make a plot of this against small r. How will it look like? Well, if r is equal to 0, the function actually is 0. If r is equal to 0, the function is 0, and as you go away from the origin, the function actually increases, then it will reach a maximum, and then eventually all wave functions, when you are far away, the wave function will decrease to 0. So, this is how the appearance is. So, the most interesting thing regarding this function is that the value at the nucleus is actually 0, but this was not the case with the s orbital. We have discussed 1s as well as 2s. In both the cases, the function was non-zero at the nucleus, and it was 0. It is 0 equal to 0 in the case of L equal to 1. We will find that this is a general case. Whenever L is equal to 0, the value of the wave function is actually non-zero. Only s orbitals have a non-zero value at the nucleus. All the other orbitals that we will see will have a value which is equal to 0 at the nucleus. Okay. So, the function is actually 0 here. You can even plot 4 pi r square, but anyway I do not think I will bother doing that. 4 pi r square, r21 square, if you want you can make a plot. Let us not do that. Now, we want to look at the angle dependence. You see, angle dependence is interesting. It contains this factor of cosine of theta. In this case, it is a little bit simple because there is only theta, there is no phi, correct. That is how it is. So, how will I make a physical picture? How can I understand this function? How it varies in different directions. What I want to see is I want to understand how this function is in different directions in space, correct. So, in general what is going to happen is that I will have y Lm theta phi, right. This is the angle dependent part. In the earlier case, this angle dependent part was just a constant, but now we have some function and I want to understand the behavior of this function. How will I do it? And the method that I am going to adopt is referred to as making a polar plot of the function. Okay. Let me imagine that I have the nucleus and I think of any particular direction in space. For example, this is my x axis, that is a direction, a positive x axis is a direction in space, and that will have the value of theta equal to how much? 9 theta is 90, right? X direction, theta is 90 and the value of phi is actually 0. So, therefore, for a particular direction in space, I know precisely what the value of theta is, I know precisely what the value of phi is. So, I can take those values of theta and phi, put it in here. For example, we just now show that for the positive x direction this is 90 and phi is actually 0. So, what I will do is, I know the functional form, into that functional form I will put the value of 90 and the value of phi which is 0. For example, if you have this function cos theta, you will put theta equal to 90 degrees and phi is not there. So, you do not have to worry about that. If you put theta equal to 90, what will happen? This will be actually equal to 0. So, you can evaluate the function, this function in any given direction in space, correct. So, when you evaluate it, what will happen that in this particular case I got the answer 0, but maybe you will get an answer not 0, maybe you will get 0.5 or maybe you will get minus 0.5, that also is possible. So, then what I am going to do is this, let us say in this direction I have evaluated the function, here is my origin, that is where the nucleus is, if you like. In this direction I will evaluate the function, suppose I get a value of 0.5. Then what I will do is, in that direction I will find a point such that its distance from the origin is equal to that 0.5, right. Now, you may ask what will happen if it is minus 0.5. Well, what I will do is I will forget the negative sign, so that the distance will be 0.5. Now, forget the negative sign, you may say, well, that is arbitrary, that why do you do that? The answer is, instead of saying forget the negative sign, I will say, okay, if the function turns out to be negative, I will take the absolute value of the function and put a point such that its distance is equal to that absolute value. So, I will do that for each direction, correct. So, in this direction I will have a point, in this direction I will have another point, and I imagine all possible directions, in each direction I put a point, and then I will join together all these points, and the result is going to be a surface, and that surface is what is referred to as the polar plot. To illustrate, suppose I made a polar plot for 1s atomic orbital. For the 1s atomic orbital, this function actually is equal to 1 by square root of 4 pi. So, in any direction you evaluate the function, answer is going to be 1 by square root of 4 pi, and therefore, what will you do? You will put a point in space in such that its distance from the origin is equal to 1 by square root of 4 pi, and then join together all these points. What is the answer? It is nothing but a sphere, surface of a sphere, and so you say that the polar plot for an s orbital is what? It is nothing but spherical, it is the surface of a sphere. This is to give you the idea. And now, what should I do? I have this particular orbital, and that for that particular orbital the function is not a constant, it is not 1 by square root of 4 pi, but it is actually cos theta, may be multiplied by a constant, but I will not worry about the constant, I just need to worry only about cos theta. So, what should I do? I should make a plot of make a polar plot of this function. How am I going to do that? Well, very quickly, let me say I have my coordinate system, this is my z axis, this is my y axis, and the way it has been put, the x axis will be like that, pointing towards you, and I am not going to show that. Okay. So, what will I do? I will first think of this direction in space. z axis, and I know that the value of theta along the z direction is equal to theta. What is the definition of theta? Theta is the angle between the direction and the positive z direction. You see, if your direction is this one, then this is your theta, remember. So, if I am saying that my point is along, I am thinking of a direction which is along the z direction, then the value of theta will be 0 degrees, and cos theta when theta is equal to 0 is 1. So, therefore, what is going to happen is that I will have to put a point somewhere here such that its distance from the nucleus, from the origin, not the nucleus, but from the origin is equal to 1 unit. This distance will be equal to 1 unit. Now, suppose you think of a direction something like that, such that this angle is 30 degrees, 30 degrees. You have to evaluate cos 30 degrees, cos 30 degrees is actually root 3 by 2, and root 3 by 2, maybe I will just write a table so that I have a ready reference to the table. I can have a ready reference to the table, theta and cosine of theta. If theta is 0, this is 1. If theta is equal to 30 degrees, the answer is 0.85. If it is 45 degrees, it is 0.7071. Actually, this will turn out to be 1 by root 2. Then 60 degrees, this will turn out to be 0.5. 90 degrees, this will turn out to be 0. So, these are the values. So, 30 degrees, what will happen? The point that I have to put is at a distance of 0.85, which will be somewhere here. Then 45, it will be somewhere here, and the 60 degrees, it will be somewhere here, right. And why should I confine myself to this side? I can also do the same thing with the other side, because for this direction also it is 30 degrees, correct. For this direction also it is 30 degrees. So, theta is 30. So, you will have one point there, you will have second point. Well, I am in a hurry because I am have to finish. Then here this one, and this is what it is. Right. So, I have marked these points, and then what should I do? I have to join together all these points. What will happen if you think of this direction? It is 90 degrees. So, the point that you will put will actually coincide with the origin. So, join together these points. So, what is the result that you are going to get? You are going to get a curve like this. Well, I am not too happy with this figure. As I always say, that is because I put the points and then joined them to form the curve. What I should have done is I should have drawn the curve and then probably put the points. So, let me modify this figure, because I want the figure to look correct. Actually, if you had made this plot, what you get is nothing but a very nice circle. It is actually a perfect circle, even though it does not appear to be a perfect circle, just touching the horizontal axis. That is how the plot is. In the similar fashion, you can continue downward. Actually, if you think of 120 degrees, you will find that it is minus 0.5. Now, you see the function is negative. If you think of 135 degrees, cos theta is minus 0.7071, 150, right. 150 you will find minus 0.85, 180 you will find it is minus 1. So, in the downward direction, that means you are thinking of directions downwards, the function is negative. And I remember what I told you, if the function is negative, I am going to take its absolute value and put points in the downward direction such that the distance is equal to the absolute value. So, then what will happen? I will get another nice circle looking identical, and these two circles, what do? They just touch each other at the origin. but then of course in these upward directions the function is positive, so I will put a positive sign here, and in the downward directions the function is negative, so I will put a negative sign there. But remember, this plot I have confined myself to a plane. What is the plane? It is YZ plane, right. It is the YZ plane that I have confined myself, but suppose I did the same thing in the XZ plane. XZ plane will be this plane, right. For the XZ plane and the YZ plane, what is the difference between the two? You see, this plane would have, well, if you are on this side, actually phi is equal to 90 degrees, well, if you are on the other side, phi is equal to 270 degrees. But if you think of the XZ plane, what will happen? The value of phi will be different, that is all. But you look at the function has no dependence upon phi. So therefore, if you made this plot in the XZ plane, what will happen? The plot will appear similar. It, in fact, if I put my hand here and plotted it, it is going to look like that. And not only that, even if you had a plane like that, the function will look the same. So therefore, if you wanted to get the actual 3-dimensional appearance of the plot, what should you do? You have to take this figure and rotate it about the Z axis. If you rotated this figure about the Z axis, you will get the actual 3-dimensional appearance of the polar plot. And what is that? It is just two spheres having their origins along the Z axis, just touching each other at the origin. Okay. So that is how it is. In fact, we have run out of time, so in the next lecture I will show you the polar plots that have been made using Mathematica. Okay. So thank you.